Hey everyone, and welcome back for this video on determining the empirical and molecular formulas of unknown compounds. First, I very briefly want to go over the definitions of molecular formula and empirical formula, and what the differences between them are, because I know that was something that was confusing for me when I was first starting to learn how to do this. So, molecular formulas are what tells us about how many atoms of each element are in a compound, whereas empirical formulas tells us the most reduced or simplest ratio of elements in a compound. Sometimes, like in the case of CO2 or H2O, the empirical formula and the molecular formula are the same. These two have a formula that's the simplest ratio of elements in a compound, but it's also the true molecular formula. It is the amount of atoms of each element that are in the compound as it exists. Sometimes, though, they are not the same, like with N2O4. This is the molecular formula, but the empirical formula would be NO2. Sweet. Now that we have those definitions out of the way, I want us to consider an example. Say that we have a compound that we know is composed solely of hydrogens and carbons, but we don't know the amount, and thus we don't know its empirical formula or its molecular formula. The first step of being able to determine both of these formulas is to first measure the masses of each of the elements in an experiment. Chemists don't innately know how much of an element is in a compound. They first have to perform some type of analysis on the compound to determine what elements are in it and how much. Well, we won't be performing the experiments, at least not in lecture. The masses obtained from these experiments allows us to perform a percent composition calculation, defined as the percentage by mass of each element in a compound. Let's return back to our discussion on the unknown compound containing hydrogen and carbon. As we can see here, our percent composition calculation would involve taking the mass of the hydrogen, which is determined from the results of this experiment, divided by the mass of the compound used in the experiment, and multiplied by 100%. This gives us the percent of hydrogen by mass in the sample. We would do the same for carbon. This is what the process will look like with actual measurements or numbers involved. See here in this example, the amount of grams of the unknown compound was 10 grams that was used in the experiment. And then our output, like the measured amount of hydrogen that we got from our experiment, was 2.5 grams. So then all we had to do was take the grams of hydrogen that was found by the experiment divided by the total grams of the compound utilized in the experiment, and then we get a 25% composition. That is cool. Since percent composition can be useful to know even when you have the molecular formula, I wanted to walk y'all through a calculation where you can determine a percent composition from a molecular or empirical formula. So this is a little bit different. We know the molecular or the empirical formula already. We just want to determine a percent composition because percent composition can be utilized in other areas of chemistry. So when we're determining the percent composition from a molecular formula, all that we're really doing is dividing the AMU of the atom in question, or of each atom, by the total AMU of the entire compound. And AMU here is like saying grams per mole. So the AMU for the entire compound, just as a refresher, can be calculated by solving for molecular mass, which was covered in the video on how to quantify matter. So for a specific atom in question, this would be the formula that you would use to get the percent composition of that atom. An example of doing this that I will outline is NH3, or ammonia. In ammonia, there is one nitrogen that is present, which is equal to 14.01 AMU according to the periodic table. There are also 3 hydrogens, which 3 times hydrogen's AMU is equal to 3.024. From the process of constructing the molecular mass, we can see that there is a total of 17.03 AMU total in ammonia. Now, we can calculate the percent compositions for both the respective amounts of nitrogen and hydrogen as demonstrated in this picture. All that we've done is we've taken nitrogen's AMU divided by the total AMU multiplied by 100 gives you the percent composition. This is the same thing that was done with hydrogen, except for hydrogen's AMU, which is 1.008, was multiplied by 3 first to get to 3.024, because there are 3 hydrogens that are present in ammonia. Now, I want to show you all how to determine the empirical formula for masses of atoms in an unknown compound, using a couple of examples along the way to illustrate these things. So, say like before, we have a compound that we know contains carbon, and we know it contains hydrogen. We want to determine its empirical formula. We've already performed an experiment, and now know the grams of both the carbon and the hydrogen in our unknown compound. We're at a good place for us to be able to determine the empirical formula, primarily using dimensional analysis. So the first thing that we're going to do is we're going to convert from grams to moles. For example, we'll say that we have, from our experimental analysis, found that our compound containing carbon and hydrogen has 1.71 grams of carbon and 0.287 grams of hydrogen. So all that we're doing here is we're using dimensional analysis in order to calculate for the number of moles of each subject. So in the case of carbon, we put, like we said, grams are on top over here, so that they have to be on the bottom here, and that way we get moles on our on the other side of the equation. And the same thing for hydrogen. We're just using the grams per mole conversion in order to get from grams of the atom to moles of it. Then we need to divide each element's molar amount, which is what we just calculated, by the smallest molar amount within the compound to yield subscripts. In our previous example, or the example we're working on, this would be carbon. Carbon has the smallest molar amount when compared to hydrogen. So we divide the molar amount of the element by the smallest molar amount. We do the same thing for hydrogen, and we get CH2. And that's our empirical formula. CH2 is our empirical formula. However, if your second step leads to a subscript that isn't a whole number, or close-ish to a whole number, you must multiply both of the subscripts by an integer so that all subscripts are a whole number. For example, let's look at ClO. The oxygen's subscript is nowhere near a number after we've completed step 2. So, we must multiply both the oxygen's and chlorine's subscripts to yield the true empirical formula. So we have ClO 3.5. So what we have to do is we have to multiply both by 2, and then we get Cl2O7, and that is our final empirical formula. Also may have to determine an empirical formula when given the percent compositions for the element in a compound. In this case, all you have to do is convert percentages to grams. Like I said, all you have to do is convert percentages to grams first, then we can solve the problem in the same way that we did earlier. For example, let's say we have a compound containing carbon and oxygen, having a percent composition of 27.29%, and oxygen having a percent composition of 72.71%. Since the scale for percentages is 100, when given this type of problem, I find it easiest to assume that the sample was a 100-gram sample in the experiment, even if it wasn't, and that the gram amounts of each sample generated for carbon and oxygen is then 27.29 grams and 72.71 grams, respectively. Then we just need to calculate the empirical formula in the way that we already know how, by first converting from grams to moles. Once we convert using dimensional analysis to our molar amounts, Then we divide the lowest molar amount to generate the subscripts for the element. Once we've generated our subscripts, we get the empirical formula, CO2. We're almost done, y'all. The final thing that we must know how to do is to derive the molecular formula from the empirical formula. So here are the steps. We're going to take the molecular mass, which is measured experimentally and would be given to you on a problem or an exam, and divide it by the empirical formula mass. The empirical formula mass can be calculated because we know the empirical formula, and we can use the same methods of calculating the molecular mass that we used in the quantifying matter video and use it to calculate the empirical formula mass using the same exact protocol. Simply put, we divide the molecular mass by the empirical formula mass to get n formula units. All that we have to do is multiply all of the subscripts from the empirical formula, which we've already calculated, by n in order to get the molecular formula. And that's it. Through an example of this concept, say that the empirical formula for nicotine is C5H7N, and the molecular mass is equal to 162.3 grams per mole. What is the molecular formula for nicotine? So the first thing that we have to do is find the empirical formula mass using the AMUs for each of the elements from the periodic table. This is what that looks like. So using the AMUs from the periodic table, I have calculated the empirical formula mass here. All that I've done is what we've done in previous videos. The amount of carbons in the empirical formula is 5, so I multiplied that by the AMU to get 60.05. Hydrogen, there's 7, so multiply the AMU times 7, and then there's just 1 nitrogen. So you add them all up, and then you get an empirical formula mass for C5H7N of 81.13 grams per mole. So I'm going to delete some things, but the next thing is to divide the molecular mass, which was given to us in the problem, by the empirical formula mass. What I've done here is I, again, have taken the molecular mass, which was given to us, and divided it by the empirical formula mass that we just calculated. And that is equal to 2n units. All that we have to do is multiply the empirical formula subscripts by 2 to get our molecular formula. So C5H7N, when you multiply all of those subscripts by 2, we get C10, H14, and 2. And that's it. And with that concludes our topic on determining empirical and molecular formulas using combustion analysis. I hope you guys have a great day, and I'll see y'all next time.